You know, so when we eased into chapter 5, see, what I did last week while we were still in chapter 4 was I went ahead and we sort of derived this equation, this mx double prime plus beta x prime plus kx equals f of t for what we set up as a mass on a spring hanging from a ceiling, a mass hanging from a spring from the ceiling, and you pull that mass and you set it in motion, and it's a mass. There's a spring constant k. The mass is m. There's a damping constant beta. And there might be some external forcing function, f of t. So we outlined all this the other day, so I just threw it up here. X is the position of the mass, the position of the mass as a function of t. So this is the general second degree differential equation that describes this motion. And there's all kinds of scenarios to pursue here. So we start, if you look at our book is broken into 5.1.1, 5.1.2, 5.1.3. So they break this down into these sort of three scenarios. And so what I want to do is start with what we call simple harmonic motion. Simple harmonic motion, which sometimes we could just call that SHM. And we would also use the phrase free undamped motion. So what I'm doing for this simple harmonic motion is I'm making it free, meaning there's no forcing function. I'm taking that away. And it's undamped, so that means there's no damping constant beta. So it really comes down to this: mx double prime plus kx equals 0. So we'll start with this guy, and then we'll add the stuff back into it as we progress. And this is pretty basic, but to do this problem, there's a lot of little subtleties going on. So I want to read a problem and do a problem from the book, and I want to do in chapter 5.1. I found one I want to do here, and it's number 8. I think I might do a couple today. I might do 8. I might do 10. There's some let's see what we got here. Yeah, I want to do this number 8. So here's what it says. I'll read it to you. Excuse me. It says a mass weighing 32 pounds stretches the spring 2 feet. Now listen, that's classic. We haven't done any of these problems yet, so this is the first one. But that's a classic sentence. I want to write that down. A mass weighing 32 pounds stretches the spring 2 feet, I think it said. 2 feet. See, that one sentence is usually how I write my problems. It's usually how the book writes their problems. And what it does in that one sentence is it tells me the mass and the K. But there's a little more to it. Listen, it says the mass weighs 32 pounds. And so what you have to remember is that weight is mass times gravity. And we're in feet per second, and so our gravity is 32. Okay, hold on a second. The weight is 32 pounds, and that's a force. And that weight of 32 pounds is my mass times gravity. But gravity is 32 feet per second per second. So I'm going to fill that in. Gravity is 32 feet per second squared. So when I put that in for my gravity, then what's my mass? 1. Thank you. My mass is 1. And it is 1 slug, actually. It's 1 slug is the unit of mass. I think we've had these discussions before. You know, it's nice to know the units, but I don't want to write units everywhere. Yeah, cool. The mass is 1. Okay, what else did it say? It said that it stretches the spring 2 feet. Well, I should remember from Hooke's law, I need to remember that the force is K times X, the distance it was stretched. Really, maybe, I'm sorry. In our derivation of this problem, we would call that S, actually, that distance it was stretched. But anyway, the force is the 32 pounds of force that stretched it. The K is this, and how far did it stretch it? 2 feet. So this is, you have to do this little preliminary work to get M and K. It's not much, but you got to get it correct. K is 16. And now you can write your DE. Your DE is 1 x double prime plus 16x equals 0. Are you guys with me? It's this DE with the M and the K filled in. And it's this initial sentence in this little initial work. It's crucial to the whole problem. I mean, it's not much. It's not that difficult, but you should understand it and be able to get M and K. You need M and K. But now you can solve this little DE. Now, this little DE probably has initial conditions. These are real problems. We really are pretending there's a mass hanging from a ceiling and we're pulling it. And so what does this say here? It says, determine the amplitude and the period of motion. They got a lot of stuff they want to ask me. If the mass is initially released from a point 1 foot above equilibrium with an upward velocity of 2 feet per second. So those are two initial conditions right there. What they told me was at time 0, they told me the initial position. And also at time 0, they told me the initial velocity. So I pulled it up 1 foot and then I gave it a little initial push up or down. What did they say? Up. Now, the other thing you have to remember from 2 weeks ago when we derived this equation is we called up negative and down positive. I'll just remind you quickly, here was our ceiling, here was our spring, here was our mass hanging on the spring, and this was called equilibrium when it hung there. And this was x equals 0, and above that was x less than 0, and below that was x greater than 0. We call down positive position below equilibrium. Still not sure why, but anyway, that's what we did in the derivation of our DE. So what are we saying? What are we saying? So that was, what was this? Initial position, 1 foot above equilibrium. So that's -1 with an initial upward push of 2 feet per second. So I think that's -2. Up is negative. It's not that hard, but it still freaks me out to this day. Up is negative. Cool. I got a DE to solve. I got a couple initial conditions. Let's do it. It's not hard. I want to change it into my auxiliary equation. In my auxiliary equation, I usually write M as my little variable, but I don't want to use M as my variable because M is mass. So I'm going to use R. So I'm going to call it R squared plus 16 equals 0. I'm going to get the roots of my auxiliary equation. R squared is -16. R is plus or minus 4i. I'm ready to write my answer. I know how to write an answer when it's 4i. The answer is, this is it. X equals C1 cosine 4t plus C2 sine 4t. X is the position, which acts like Y, sort of. T is time, that's, okay, X is a function of time. Well, cool. I can probably, use my initial conditions to find C1 and C2. To do that, though, I guess I need X prime. Let's just go ahead and get X prime. The derivative. The derivative of cosine. -4 C1 sine 4t and +4 C2 cosine 4t. Yeah, that's it. Chain rule spits out a 4. Okay, this isn't too hard. Using these initial conditions, I'll find C1 and C2. If you plug in a 0, the position is -1, okay? If I plug in a 0, the sine of 0 is 0, the cosine of 0 is 1, and you just discovered C1. And I think that's usually how it goes in these simple harmonic motion problems. C1 is that initial position. But C2 is not quite that number. Due to the chain rule, you can see what happens. To get C2, let's see. This x prime is going to have a value of -2. That's my velocity, initial velocity. When t is 0, that's 0. That's a 1, but I get a 4 C2. Okay, so when you divide by 4, C2 is -0.5. All right, well, I got them. So my position is -1 cosine 4t and -0.5 sine 4t. How you guys doing?
Pretty good.
All right. Hey, that's the answer. Maybe I could sketch it in my graph, check out a graph of this. I'd watch it. It would be a beautiful sine wave is what it would be, or cosine wave, or you know what it looks like is it looks like it's the sum of 2 sine and cosine waves. It is, you know, but they both have the same frequency. They both have the 4t, which dictates the period or frequency, that 4t. So really, see, here's the thing. We don't want to leave our answer like this. For future computations and so forth, we want an alternative form. And this part gets a little tricky. I mean, it's not. But I don't want to leave my answer like this. I mean, it's an answer, man. It's the position equation of this spring, of this mass. It's the position equation of this mass. But I want this alternative form. The alternative form is this. Capital A sine omega t plus phi. Where this capital A is actually the amplitude, and the capital A turns out to be this formula. The square root of C1 squared plus C2 squared. It's kind of interesting. It's almost like a Pythagorean theorem. That A is C1 squared plus C2 squared. The omega is the coefficient on t. Guess what? It's the same old omega from the problem. What is the omega in the original problem? The 4. The 4t? Yep. So the omega matches the 4t. So there's not a debate on what that is. But we calculate A, which by the way, like I said, that's going to be the amplitude of this thing. And then this phi is some kind of a phase shift. This angle phi is a phase angle or phase shift. And, oh boy, how do we do this? I think we say that the tangent of phi is C1 over C2. Let me make sure I have that right. I don't want to get it. Yeah, that's right. Okay. So then I guess I calculate phi by taking the tangent inverse. You got to be careful when you hit tangent inverse on your calculator. Why do you got to be careful with tangent inverse on your calculator? Does anybody remember the story? Yeah, your calculator only gives you answers in first and fourth quadrant. And depending on what C1 and C2 are, you may be in quadrant 2 or 3. See, the picture that sort of goes with this, these formulas, is this picture maybe. Watch this. C1, C2, sort of like a triangle here. This amplitude is A, and this is the phase angle phi. I mean, right, you guys? What's the hypotenuse of this triangle? Square root of C1 squared plus C2 squared. Right, that which we'll call A. And then that angle is phi. What's a little dangerous is C1 acts like a Y value here. It's very tempting to put C1 on the x-axis. I guess you better not do that. C1 should be on the y-axis, C2 should be on the x-axis for this to make sense, because that's opposite over adjacent. And the truth is, depending on what C1 and C2 are, it could be in quadrant 1, 2, 3, or 4. So like I said, if you use tangent inverse on your calculator, you may have to make an adjustment to be in the right quadrant. Well, here we go. So I want to put this in the alternative form. So I want to calculate A. What's my C1 and C2? My C1 is -1, and my C2 is -1/2. So this is -1 squared plus -1/2 squared. This is my amplitude. 1 plus 1/4, I guess that's 5/4. The square root of 5/4. How about the square root of 5 over 2? That's my amplitude. The phase angle would be, the tangent of phi would be C1, -1 over -1/2. Okay, that's actually the tangent of phi is a 2. That's what that is. That's a 2. So phi is the tangent inverse of 2. The tangent inverse of 2, but that's going to be an angle in quadrant 1, and I should realize that with that -C1 and -C2, I'm really, in this particular problem, I'm in quadrant 3. I got -1/2 for C2 and a -1 for C1, and I'm in quadrant 3. Do me a favor, I want this in radians, and I want it rounded off, though, to like 3 decimals. What is the tangent inverse of 2? In radians, rounded off to 3 decimals.
1.11.
1.11.
1.107, sorry.
That's okay. 1.107. Okay, that sounds right. That's it. And by the way, that is in quadrant 1. You know, I happen to know that 1 radian is roughly 60 degrees. 1 radian is roughly 60 degrees, and that's roughly what that is. That's in quadrant 1, and I don't want to be in quadrant 1. I got to make the adjustment. I got to put myself in quadrant 3. How do I do that?
Add pi.
Oh, add pi. Yes, add 180 degrees or add pi. Okay, so this is not the proper phi until you add pi. Go ahead and add pi and round it to 3 decimals, and your phi is this.
4.249.
All right, thank you. All right, you guys, we did it. We found the amplitude, we found the phase shift, and what we can do now is write this position equation in its alternative form. There it is in its original form. But we did this extra work to write it in this alternative form. The amplitude is the square root of 5 over 2 sine 4t plus 4.249. You know, I used to bring my graphing calculator to class, and I used to show you guys my graphing calculator a lot more often than I do. I used to have a nice little tool for that, but so I'm not doing that near as much as I used to, but I wouldn't, you know, what would be cool is if you type this in your graphing calculator or type this in, they're the same thing. These are the same. That's why it's an alternative form. This is the same exact graph. And so maybe you never knew that before, that the sum of a bunch of sines and cosines is really just a sine function. But it's with an amplitude and a phase shift. So they're the exact same graphs. Yeah. And I kind of know what they are. I mean, well, it does have that phase shift. Let me think. You know, when I read the problem, hang on a second. When I read the problem, oh, here it was. What was this initial position? The initial position was -1. That's right here, right? By the way, that's above equilibrium. I know, it's weird. But that's how it got started. And then, did it have an upward push? It had an upward push. That's up, right? So it had an upward push. So it started here, and somebody gave it an upward push, which gave it a little push this way, and then it fell into its motion. And it's simple harmonic motion. It's a beautiful sine wave. It's got a consistent period or frequency. It's got a consistent amplitude. It doesn't lose amplitude. It would lose amplitude if it was in a damped environment. But we're not in a damped environment. We're in this ideal world where this thing's just going to oscillate forever at that amplitude. By the way, the square root of 5 over 2 is roughly, well, there it is. That's the amplitude. A little over 1, all right? Let's answer a few questions here about this graph. What is the amplitude? Right. So what is the amplitude? Square root of 5 over 2, and it is in feet. It is feet. Okay. What is the period? 2 pi over 4, or pi over 2. And that's seconds. That's pi over 2 seconds. Period is seconds. Hey, what is the frequency? And we haven't used that term much, but the frequency is the reciprocal of the period. It's 1 over the period. It's 2 over pi, I guess. See, the period is the number of seconds it takes to do one cycle. You can say one cycle or one oscillation or one revolution. Depends on how you're talking. We're not really talking about revolutions here. The period is the time it takes to do one cycle. So this is this many seconds per cycle. And the frequency is the reciprocal of that. So this is how many cycles it does per second. So it does this many cycles per second. You with me? They're reciprocals of each other. Their units are reciprocals. All right. They often ask me this question. This is what we do. The DE is over. We solved it a long time ago. But we spent some time getting into this alternative form, and now we're graphing it. We're getting a bunch of details. We get real detail here in Chapter 5. I want to know all this information. I want to know this question. When does it pass through equilibrium? When does it pass through equilibrium? And I just erased my original form. Anyway, what should I do? When does it pass through equilibrium? What should I do?
0.
Set it equal to 0. Right. Set the position equal to 0. But, you know, a few minutes ago I had that other form, what was it? Negative cosine 4t and 1/2 negative 1/2 sine 4t. I mean, if you try setting this equal to 0 and working with this and solving this, it's tough. And by the way, also look at it. Can you see the amplitude right here?
No.
Not really. I mean, no, you can't. I mean, you now know that you take that C1 and that C2 and you do this fancy little formula to get the amplitude. But when you write it in this form, you can see the amplitude. This form, you can't really see the amplitude. And you can't work with it that well. Setting this equal to 0 and trying to solve kind of sucks. With the cosine and the sine, yeah. I mean, maybe you run into some tangent. Anyway, I'd rather set this equal to 0. Watch how cool this is. When you set this equal to 0, it breaks down to this. You can divide by the amplitude if you want. I'm going to save myself that step. But you can divide by the amplitude. And then you're asking yourself, when does a sine function equal 0? When does a sine function equal 0? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, negative 2 pi. When does the sine function equal 0? And so wait a minute, we're just shouting out that whole list of angles there. So we're saying this equals 0 when that angle equals 0 or pi or 2 pi or 3 pi or negative pi or negative 2. You with me? Yeah. All right, now here's what I'm really looking for. I'm looking for that first positive time. So watch. I wrote this whole list here because what if you just set it equal to 0 and tried to solve it? If it was just equal to 0, well, you'd move this 4 over. It'd be negative. You'd get this negative time, which we don't want. I mean, everything starts at time equals 0 here. This is my time axis. Everything starts at t equals 0. Yeah, so I don't want to set it equal to 0. Okay, what if I set it equal to pi? Well, let's subtract the 4.249. Yeah, that's negative. See, because of that phase shift, this is kind of tricky. You got to figure out apparently all these angles are going to generate a negative time. Okay, here we go. I think I should set it equal to 2 pi. And now when I subtract the 4.249 and divide by 4, that's my answer. Subtract and divide by 4. That's my answer. That's my answer to this question. When is the first time it passes through equilibrium? Is that what I asked? No, not exactly. When is the first time it passes? Well, we got it. And go ahead and decimalize, you guys. We're in a word problem. We can decimalize some of these things here. What is this? Can you help me? What is it?
0.509.
Okay, thank you. I'll call it 0.51 seconds. Yep, that's it. Wait a minute. Let me just make sure. That's the first time. Hey, by the way, you can confirm all this again if you took the time to bother to put it in your graphing calculator and take a look at it. You could, trace your way over there or use your root feature. Anyway, you could find out that you could confirm this kind of using a graphing calculator. You can confirm some of your math. If we want to be, kind of mathematical about this, but technically the question was, when does it pass through equilibrium, which has an infinite number of answers? And if I wanted to list all those infinite number of answers, I could start with this first time and then add, what'd you say?
A period.
A period. Well, you know what? If I add a period, that'll give me that one. Maybe I should add half a period. Okay. If I add half a period, I'll get that one, and then another half a period, and another half. You're right. What was the period? Pi over 2. So you're saying all the times it passes through equilibrium are this 0.51 plus n pi over 4, because that's half a period, for n equals 0, 1, 2, ... That's our fancy way of writing all the times. You guys can read that, okay? Is that okay? Mm-hmm. It makes sense, right? I'm adding a bunch of half a periods. Cool. Good job. All right, I got more questions on this. I could say there's a lot of questions. There's a nice question, number 11. It has a part A, B, C, D, E, F, G, H, I, J, K, L, M. Wait a minute. I should have stopped at K. Sorry. A, B, C, D, E, F, G, H, I, J, K. It has. So we do one problem. We can answer. We can ask all these questions, kind of like this: A, B, C, D, E, F, sketch the graph. I mean, I don't know. There's a lot of little things you can do. Once you solve the D, you can analyze the hell out of it, is what I like to call it. Like, here's what I want to know. I'd like to know the velocity of this motion at the moment it passes through equilibrium. I want to know, so how do I write? I'm going to write that question. Find the velocity of this mass.
We're still on the ring.
Yeah, I'm still on of this mass. Find the velocity when it passes through equilibrium. When it passes through equilibrium. You know, you know, when you're staring at a position graph, the velocity is the derivative. And so I can take a derivative and get a velocity equation. Hang on. What I was going to say is staring at the graph, so if the velocity is the derivative, then the velocity is the slope of the tangent line at any point. So you can kind of think about the velocity at any time you want, you know. So when does this velocity look like it's the steepest or the
Changes in inflection.
Maybe at the inflection points, which I would say are at equilibrium. I mean, you know, this mass started off with initial push, you know, gravity and the restoring force of the spring pulled it back toward equilibrium, and it was hauling ass right there. It was hauling ass, but then, you know, the spring was slowing it down. I think, right? It reached a max, and then the restoring force of the spring pulled it back through. So I think it reaches its maximum velocity at these places. You're right. That's where the tangent line is steepest. You know, what's the velocity right there? Zero, right. For just an instant, it stops at those extreme places. Just for an instant, it stops as it turns direction and heads the other way. Our velocity is positive and negative, depending on whether we're heading up or down. Up is... Up is negative. In our problems, up is negative. On the graph, yeah, see, now I'm going to get confused. Hang on, let's do it. Find the velocity at the time when it passes through equilibrium. Okay, so I want a derivative. The derivative, again, the derivative is a little easier than it was with the original form of the answer. It had the sine and the cosine in there. Here's our answer right here. It's easy to do this derivative. The derivative of a constant multiplied by a sine, you just hold the constant, you take the derivative of sine, and it's cosine. The chain rule spits out a 4. The 4 is going to come out front, I guess. You could call that 2 square roots of 5 cosine 4t plus 4.249. Are you guys with me? I took that derivative. The derivative of sine is cosine. The chain rule spit out a 4 that multiplied out front. Huh. Hey, remember this little 0.51? Remember this little time? This is the time when it passed through equilibrium. Is that what this was? Well, what did that do? That made... It made this argument equal to 2 pi, right? Is what... All right, so if I plug that time back in here, it's going to make this 2 pi. What's the cosine of 2 pi? 1. So at t equals 0.51 seconds, when you take that time we just found and plug it back in here, it makes this a 1. It makes it this speed, feet per second. And it's positive. It is heading, okay, on the graph, it's heading up. and it's a positive slope, and it's a positive velocity.
It's heading down and around.
Yeah.
In life,
It's going down.
Yeah.
it's going down, and down is positive.
Yeah.
Wow. Yeah, the graph. The graph is an upside down version of real life. Your book has a little illustration of that. They got the mass hanging from the ceiling, and then they say, this is an inverted picture of that is the picture we get here. Anyway. Positive is below equilibrium. This whole area is below equilibrium. This whole area is above equilibrium. And at that moment, I'm heading down very fastly with a nice positive velocity. Find the velocity of mass when so this is going to be the velocity every time it passes through equilibrium? Is this the velocity every time it passes through equilibrium? Except for the sign change, exactly. So there's a little glitch there. Yes, every time it passes, this is it. And this is the fastest speed it goes. But again, at this time, it's going to be negative 2 square roots of 5 feet. And this one's going to be positive. This one's going to be negative. This one's going to be positive. It's either a positive or a negative slope. It's either heading down or up. It's positive or negative velocity. Well, what's my, So at this time, the answer is positive. So let me change my question. Find the velocity of mass when it passes through equilibrium the first time. Let's change it to that. And if I add that, then what's the answer? This.
If you just wanted the speed, it's the magnitude.
Right. I could have, and then I would use the word speed. I should use the word speed. Yeah. All right, you guys. That's pretty good stuff. I mean, it's a lot of information. The book says, what did we do? We built this alternative form. I'm assuming. We built this alternative form, A sine omega t plus phi. And we're going to use this alternative form. We're not going to, but the book mentions that, be aware that different scientists and engineers and different professors, different courses, might prefer another alternative form, which is this, A cosine omega t minus phi. And then there's some small adjustments that you use to get this. And I think I remember this, your physics book probably uses this when they study harmonic motion. They use both, actually? Huh. Okay.
Then we can analyze it.
Yeah, figure out why.
Yeah.
You just have what, pi over 2 or something like that?
Well, I don't know, yeah. Okay. We're going to use this one, though. But the real point is, any cosine function plus a sine function can be put into a single sine or a single cosine function with a phase shift and an amplitude. That's kind of the big point, is that we take this and put it into an alternative form. Hey, for those formulas to work, for this alternative form to work, and that C1 and C2 to get that phi right, didn't we say that the tangent of phi was C1 over C2? And then when I drew the picture, this is weird, I drew C1 on the y-axis and C2 on the x-axis, yeah. This is good, but I'll tell you what, for all that to jive, listen, C1 should go with the cosine and C2 should go with the sine. When we write our original, I mean, it never mattered. It never mattered before, right? It didn't matter how you wrote this. But I'm suggesting now the C1 with the cosine, the C2 with the sine, that's what leads to this memorized thing that leads to phi here. So we're going to do it like that. Okay, hey, let's try another one. I was thinking about trying 10. 10. Let's do 10. So, it's probably pretty similar. Maybe I won't analyze the heck out of it. Maybe I won't do everything, but I'll do some stuff here. 10 in the book. It says, it's funny the way they word this one. A mass weighing 10 pounds, a mass weighing 10 pounds stretches a spring 1/4 of a foot. So hang on a second. A mass weighing 10 pounds. That means the mass weighs 10 pounds. That's mass times gravity. So the actual mass is 10/32s of a slug. You follow me? Now what else did they say? It stretched it, that 10-pound force, which is the mass hanging there, stretched the spring, what did it say? It stretched it 1/4 of a foot? I think it said. Yeah, hey, you need to be in feet. When it says it stretched it 6 inches, you got to be in feet. You got to be in feet. This said 1/4 of a foot. Okay, cool. So what's K? So now I'm ready to write my DE and go to town. Now hang on. If I read the next sentence, they're really messing with me. Look what they say. The mass is then removed and replaced with a mass that's 1.6 slugs. All right, so they told me this. They told me this about this 10-pound mass to really just help me find K. Because then they removed, so this ain't the mass I'm dealing with, so this was a waste of time right here. They removed this. They put this mass on just to help me find K. Then they removed that mass and put a real mass on there that they said is 1.6 slugs. So it's 1.6 slugs. You guys with me?
Yeah.
It's kind of a weird little way of presenting that problem. But now, I got it, man. I got a little DE. The DE is 1.6 x double prime plus 40x equals 0. These things are always solved the same way. I mean, you could memorize some formula here. You could memorize that you're going to move the K. Oh, hang on. It's 1.6 r squared plus 40 equals 0. You know, every time you're going to move this K over, you're going to divide by m. R squared is going to be K over m. Are you with me? R squared is going to be K over m, and then you're going to take the square root. Oh, I did lose something. There's a negative sign, and that's crucial because these are imaginary answers. That's what leads to the sine and cosine, right? You got to have these imaginary answers. Hey, what is this when you divide? Go ahead and divide it. It's probably a nice number.
25.
It's 25, huh?
Yeah.
So your answer is plus or minus 5i, I guess, huh? Awesome. Because he said that was 25. Yep, cool. Well, I went ahead and started solving my DE. Sometimes it's, I like to, it's smart. When you write the DE, it's kind of smart to put the initial conditions with it. I kind of got going a little fast. What are these initial conditions? It says it is initially released from a point 1/3 of a foot above equilibrium. Hold on. X of 0 is 1/3 above equilibrium. Above equilibrium is negative. And it probably had an initial velocity. Although sometimes they just say you just let it go or you just released it, which means the initial velocity would be 0. But usually they give it some push. Here, let's see. Release from 1/3 with a downward velocity of 5/4 feet per second. So that's a positive 5/4. Okay, initial position and initial velocity. This is my position. I got my 5i, so here I am, C1 cosine 5t, C2 sine 5t. Yeah, same game again. Same game again. I'll take the derivative. Negative 5 C1 sine 5t, positive 5 C2 cosine 5t. I'll use my initial conditions. When I plug in a 0, the x is a negative 1/3. When When you do plug in a 0, the sine of 0 is 0, the cos of 0 is 1, and you get C1 is negative 1/3. I think that's rather typical. Let's see how you can change that. But C2 is, let's see, when you plug in a 0 for the derivative, you get 5/4. When you plug in a 0 for the derivative, you get this 5C2 over here. This is gone. So C2 is 1/4. I just want to draw a little picture and see what quadrant I'm in here. The C2, I got to remember, the C acts like the X. So that means I'm over here 1/4, and then I'm down negative 1/3. Anyway, so that's good to know. My phi is an angle in quadrant 4. I'll just go ahead and find it. The tangent of phi is the C1 over the C2. The C1 over the C2. And I can trust my calculator will give me an answer in quadrant 4 this time. It's the tangent inverse of 4/3 is what that is. Negative 4/3, sorry. Negative 4/3. And in radians to 3 decimals, that's
negative 0.927.
Negative 0.927 radians. Cool. That's my phase shift. My amplitude is good old square root of the C1 squared, that's 1/9, and the C2 squared, 1/16. Get a common denominator. I mean, you can, I do, sometimes I like to work with this purely here. I think that's 25 144ths.
5/12.
5/12. I'll be damned. Yes?
If we didn't want to work with negative radians, could we have just added 2pi and use that?
Yeah, you are right. I mean, I'm about to write my answer here, and so my answer is x equals 5/12 is my amplitude, sine of omega. What is omega?
Omega is 5.
That's the 5t, right? That's the, and then I'm going to put, I like the negative 0.927. If I'm in quadrant 4, I like that. But what you're suggesting is, on a unit circle or on a, that angle, negative 0.927, if you add 2pi to it, you can name it a positive name. Which would be what?
5.356.
5.356. 5.356. Now, would there be any difference at all? I don't think so. I mean, the graphs are the same. It's not, it's this, yeah, it should be the same. But why do that? I mean, why? Just because you didn't like the fact that it was negative.
Yeah.
But, right, but, okay. See, there are times when we have to make the adjustment by adding a pi, or subtracting a pi perhaps, or adding, right? And then there's the times we don't have to make an adjustment. Like now, we don't have to make an adjustment, but you just like doing it, so maybe you want to. All right, cool. Again, simple harmonic motion forever. What's their question here? Oh, they got a lot of good questions. Okay. You know what I'm going to do? I'm going to quit here. I mean, I got 10 minutes. I want to I want to preview what's coming next, but I'm not going to get too far with it. But I'm going to give you a darn good preview. Previews are always the best part of the movie anyway, right? So here comes a... Depends on the movie. But the movie sucked, but the previews were good. So if we move into damping, then that would be the next. We get out of simple harmonic motion, and now we would deal with this. And like I said, I'm not going to do a problem. But I'm going to outline some situations here for you. But you see what just happened? We just added damping to the problem, and those are fun to do. But it still has this free motion, no forced motion. So this is, you know how to solve this. You write your auxiliary equation. Your auxiliary equation might look like this. Now here I am doing this in general. Am I doing this right? My variable is too many letters up here. My variable is r. If I want to solve for r, I think I would do the quadratic formula. I just want to say that I would get negative beta plus or minus the square root of beta squared minus 4mk all over 2m. So, I'm getting the roots to a quadratic equation. So this is the damped situation, the roots to a quadratic equation. Now, let's analyze this. When you have roots to a quadratic equation, what kind of roots can you have? If the beta squared minus 4mk is less than 0, that's one scenario, right? When this is less than 0, we get a negative number in the square root, and that leads to imaginary answers. Okay, and so hang on. That leads to two complex roots. I'm going to say complex or imaginary roots, which are like, alpha plus or minus beta I. I better not say beta now. Hang on. I'm going to say A plus or minus BI, like my complex roots. And then how would I write my answer? You guys remember how to write your answer? X equals e to the AT C1 cosine BT C2 sine BT. Right, you guys?
Yep.
Right. Now, if we had some real numbers, then it would be cool to plug this in and look at a graph of this. And here's the other thing. I guarantee you, in these real situations, okay, listen, yeah. In this real world problem, you guys, the M and the beta and the K, they're always positive constants. None of them are ever. You don't have a negative mass. You don't have a negative beta. You don't have a negative. They're all positive constants. So hang on a second here. If they're positive constants, then this is negative. This is the real part. I want to say that this A is going to be negative. It's going to be negative. And if it's going to be negative, then you're going to have a diminishing amplitude. Can you look at this like our sine wave? Except now it's got this amplitude that's exponential, which you might think, holy shit, that's a big amplitude, or it's a growing amplitude. But what I'm saying is it's opposite of that. It's got this negative number here, and so it's a diminishing amplitude, which totally makes sense in a damped environment. And you get this picture. You get oscillating motion with a diminishing amplitude, and technically it does that forever. And it's somewhere down there. It's barely oscillating, but technically, it's still oscillating as it hovers around equilibrium. And this is damped. And to tell you the truth, this is kind of our classic picture of damped. But this is the least damped situation. We call this underdamped. So this is the picture for underdamped. This is the equation for underdamped. And how do you get underdamped? You get underdamped when you have these two complex roots. So two complex roots leads to this equation. It leads to this underdamped scenario.
I thought it was only whenever A was negative.
Well, A will always be negative is what I was trying to
okay.
say. I didn't do a good job of saying it. But this number will be negative, and it'll always be this. Yes. Yeah. Okay. What else could happen?
Real can equal 0.
Right. So b squared minus 4mk could be greater than 0. And if it's greater than 0, that's your two real roots. And do you remember how you write your answer for two real roots? X equals C1 e to the
whatever.
I'll call it R1t and C2 e to the R2t. Those are my roots, R1 and R2, if you don't mind. Yeah, right? That's what you get. And we haven't looked at a graph of any of those in a while or ever, maybe. But I'm going to tell you right now what kind of graph that looks like. That is this. That is this. Either, here's what they say. This is very damn damped. They call it overdamped. This is the most damped situation. And here's what they say. It may not ever make it through equilibrium. It may not pass through equilibrium ever. It's so damn damped. Or, if it does make it through equilibrium, it'll never make it through again. It'll only pass through once and then head back toward equilibrium. It just dies out. It just dies. We call this overdamped. And it comes from the two real roots. Okay, so there is one more scenario. What is it? Yeah, when the discriminant, beta squared minus 4mk, when it equals 0. And when it equals 0, what does that mean?
One real root with a multiplicity.
Good, yes. One real repeated root is what I'll say. But you're right, one real repeated root. And when it's just, an R1 with multiplicity 2, or a repeated root. And how do you write your answer then? C1 e to the R1t.
C2x e to the R2.
Yes, or t e to the R1t, right? When you have your repeated root, you put on this extra t to avoid dependency. Right, you guys? Okay. Check this out. This one's not as interesting. Those are the two interesting. I mean, here's the deal with this one. When you graph one of these, it actually looks a lot like overdamped. It either crosses through equilibrium, but if it does, it's at most once. So then it comes back and dies out. Or maybe it doesn't even cross through equilibrium. Maybe it just dies out. It's a lot like overdamped, but it's not. I mean, the graph looks like it, but the classification is called critically damped, which kind of makes it sound like it's more damped, right? Here's what I think here's what I'm going to say. The word critically damped applies to this. Listen, it applies to this discriminant equaling 0. It's like you're in this situation, but you're on the critical edge. Listen, with a small adjustment in beta, m, or k, then this thing won't be 0. Some small change in beta, m, or k, and it's greater than 0 or it's less than 0. You're sort of hovering on the critical edge between overdamped and underdamped. Are you with me? I mean, the numbers, beta, m, and k, are right there on the critical edge that makes it 0, and it's hovering between underdamped and overdamped. And it's got its own classification called critically damped, and the truth is it looks a lot like one of those, right? It looks a lot like overdamped. So the critical kind of refers to just the fact that it's just right on this edge. But that's it, man. This ain't too bad. Of course, this is kind of the toughest one. It's also kind of the funnest one. But yeah, so I've outlined this for you. I want to, but we should do a problem, and now we're luckily out of time. So you should try a little homework in 5-1, but I'll come back here Thursday and I'll have some tests graded for you. But I'll open with some more problems unless you got some questions.